In this lesson we will discuss OPAmp characteristics. The block diagram shown represents the functional contents of an OPAmp. The first stage includes the differential amplifier. It is used for the determination of the input impedance figure and uses differential inputs. Many OPAmps contain multiple differential amp circuits cascaded together, thereby enhancing the amplification of differential inputs and voltage gain. The second stage consists of the voltage amplification circuitry. This may contain a differential amplifier stage or single transistor stages in common emitter or common base modes for achieving voltage gain. Output current is small. The third section provides the current gain required to supply large output currents to fairly small load impedances without loss of output voltage amplitude. Most OPAmps use a direct coupled push-pull amplifier circuit as the final output section. Let's discuss some typical OPAmp characteristics. Gain. Most OPAmps provide gains of about 100,000. A good OPAmp has a high open loop gain. A typical value is 50,000 to 200,000. Common mode rejection ratio, or CMRR. Good OPAmps have a CMRR which is very high. CMRR is calculated by taking the open loop gain dividing by the common mode gain. In decibels, CMRR is equal to 20 times the log of the open loop gain divided by the common mode gain. Or CMRR in dBs is equal to 20 times the log of the CMRR in decimal form. Conversely, CMRR in decimal form is equal to 10 to the dB divided by 20 power. As an example, convert a CMRR of 200,000 to decibels and convert a CMRR of 1 million to decibels. The solution is CMRR in dB is equal to 20 times the log of 200,000 or 106 dB. And for the second problem, CMRR in dB is equal to 20 times the log of 1 million or 120 dB. Next, convert a CMRR of 100 dB to a decimal and convert a CMRR of 130 dB to a decimal. CMRR is equal to 10 to 100 divided by 20th power, or 10 to the 5th power equals 100,000. In the second case, CMRR is equal to 10 to the 130 divided by 20th power, or 10 to the 6.5 power equals 3,162,278. Another characteristic is input offset voltage. Since no two transistors can be exactly alike, a tiny output voltage will be output by OPAmps. This small offset is mainly due to differences in barrier potential and gain between the transistors in the first differential amp stage. Amplification of this difference by the rest of the OPAmp results in the presence of offset voltage at the output. Input impedance. Typical OPAmps offer input impedance values which are usually in excess of 100 k ohms. Use of Darlington pairs usually provide input impedances greater than 1 megohm. Output impedance. In reality, all sources have maximum current limitation and hence definite output impedance levels. In common types of OPAmps, a typical average value of output impedance would be approximately 100 ohms. Slew rate. Since transistors work through control of moving charges that can neither start or stop instantaneously, current charges will occur gradually, imposing minimum time delay. Similar delays are exhibited by OPAmps, which contain transistors. Typical slew rate figures range from 1 volt to several volts per microsecond. The slew rate is given as the change in the output voltage divided by the change in time, where the change in output voltage is equal to plus V sub max minus the quantity minus V sub max. Looking at an example, when a pulse is applied to an OPAmp, the output voltage goes from minus 9 volts to plus 9 volts in 2 milliseconds. What is the slew rate? The slew rate is equal to the change in the voltage output divided by the change in time, or plus 9 volts minus the quantity minus 9 volts divided by 2 milliseconds, or 9 volts per millisecond. Another characteristic is frequency response. All amplifying devices function only over a limited range of frequencies. The majority of OPAmps are designed for low frequency use. Low frequency roll-off in amplifiers is usually caused by DC blocking coupling devices such as capacitors. Typical OPAmps offer frequency response characteristics from 0 Hz DC to upper limits of approximately 100 kHz or more. Input signal limitations. In normal applications, input amplitudes should not exceed the DC supply values since transistor breakdown can occur. The supply values for AC and DC should be below the positive supply value and above the negative supply value.